And we're live. Hello, everyone. I'm happy to see you here. Of course, I cannot see you here, but I know that you are there. And you are here for the next installment of the Virtual Jug online Java user group, the presentation. This is the first one in 2018, and this is amazing. And we have Simon Brown here with us, and he will be speaking about software. So, Simon, how are you doing?
I'm very good. Thank you. Yourself?
Thanks. Before we start, let me just quickly share my screen and tell you a couple of things about the presentation that we're going to see and some organizational notes. So today's session is visualizing software architecture with the C4 model. And our speaker is Simon Brown. You can find him on Twitter. He goes by @SimonBrown. So he's the Simon Brown of our universe. And yeah, he's an independent software architecture consultant, author of multiple books. And I'm sure if you have any questions about software architecture or team leadership or anything, he will be happy to help. If you have any feedback about the session, the whole community is joining our Slack group. You can find that on the website, virtualjug.com. There will be a button, join Slack. There is a channel for live session. And if you have any questions to Simon, you can just post them there. I will try my best to forward them to Simon. Obviously, please share this session or the meetup community for the Virtual Jug. And if you have any feedback, then Virtual Jug on Twitter or just post directly to me @Shalive, and I'll be happy to see that we resolve any issues. One last thing, if you have the video quality that is not up to your expectation, the cog icon below the video and increase the quality. So it should go up to HD. So you should do that. Anyway, with all that organizational stuff out of the way, let me stop sharing my screen. And Simon, you're now live. People can see you, and you can say hi to everyone and share your screen and start the presentation.
Superb. Will do. Thanks very much. Hi, everybody. I hope you're having a good evening or morning or whatever, wherever you are. So I'm going to share my screen now, and we'll start the slideshow. Hopefully.
Yep.
That.
I can see a video of a handsome person there, and now I can see the slides.
And now it's gone, thankfully.
Excellent.
So,
there you go.
So this session is going to be about software architecture and specifically visualizing software architecture with something I created called the C4 model. For those of you who don't know me, I'm the author of a bunch of books. Most recently, I've created a couple of books called Software Architecture for Developers. I also contributed something to Uncle Bob Martin's Clean Architecture book recently. And way back in the past, I wrote some Java books that we don't talk about anymore. So I'm an independent consultant now specializing in software architecture. And one of the things I do on a regular basis is I get to fly around the world and visit organizations, and I set them architecture charters. And essentially what this means is I give groups of like 2 to 5 people some requirements. I say you have 1.5 hours, 90 minutes, go away, do some design, and then draw some pictures to somehow visualize the solution that you've come up with. So in essence, draw some software architecture diagrams. This seems like a fairly easy thing to do, but it turns out that it's actually really tricky in the real world. And so I asked people, what did you find specifically challenging about doing this exercise? And they always say things, well, we're in a classroom, we need to verify our assumptions and all that sort of stuff. But in terms of expressing the solution itself, we're not really quite sure how to do that. So we're not sure what types of diagrams we should be drawing and what notations we should be using and what level of detail we should be going down to, and so on and so forth. And when I'm wandering around the classroom and I'm listening to groups and what they're saying, I'll often hear people actually say this, they'll be drawing a box or a shape or a funny symbol, and they'll say, this does make sense, but we'll explain it later. And there's always this weird perception that you're going to present your architecture diagrams during an architecture charter workshop. And that's not what I do, because it's far too simple. So what I do instead is I get people to switch diagrams. And what this highlights very quickly is that each group has a bunch of information that's still stuck in their heads. And this kind of makes sense, right? Because they've been working for an hour and a half. They've been having conversations in their groups. And once you give the artifacts, the architecture diagrams to a different group, well, there's stuff missing. We're essentially switching the context. We're removing the authors from the artifacts. And then once we've switched diagrams, I ask people to review the diagrams. And they often say things like, well, we don't really know what the diagrams are showing. We don't know what the shapes mean. We don't know what the arrows mean. We don't know what the color codings mean. We're not really sure what the boxes represent. And sometimes if a group is given a collection of diagrams, they're unsure often which diagram to read first. So here are some example diagrams. The set of requirements is for a financial risk system. And it's very simply, imagine you work for a bank and you need to create some sort of risk system. There is a trade data system. So this is a source data system. It has a list of trades that the bank is making with other banks. There's a reference data system, and the reference data system contains lists of other banks that you do business with. And essentially, the financial risk system takes these two data sources, merges them together. It performs some little black box calculations, and it creates an Excel report. And there's also the ability for users to customize the parameters used in the risk calculation. So this example here is a real diagram from a real workshop. And it doesn't really tell you anything. It's just a named collection of boxes showing technology choices. So, Unix and Windows, JBoss, and Microsoft SQL Server. It's nothing more than a bulleted list in a diagrammatic format. This is one I called boxes and no lines. So this one has boxes, but unfortunately no lines linking things together. So at the top, there's an ASP.NET web application, which I guess is doing something, but there are no users using it, which is a bit weird. At the bottom, there are a bunch of SQL Server things. I'm guessing these are databases, but they could be schemas or tables or views. And then there are a number of boxes in the middle. And the number of boxes in the middle are really the next level of decomposition into the solution space. So there's a logging service and a risk calculation thing and a report generator thing and a data import thing. But there's nothing telling you about the structure here. There's no lines linking these boxes together. This is what often people draw, and they call it a functional view, and it's just a list of stuff. And again, it doesn't really tell you that much about what the system is doing. There's also a tricky color coding to decipher here, the red text, the blue text, the green text. And the honest answer is I don't know what the color coding means. It could mean anything. It could mean stuff we're building versus stuff we're buying. It could be ownership by team or person. It could be infrastructure versus business. There's a whole number of ways we could explain the color coding. This one here is one of my all-time favorites. It's often what I refer to as the airline route map. So next time you go up in an airplane, grab the in-flight magazine and turn to the where does this airline fly to, and you'll get a picture like this. So the central spine of this diagram kind of makes some sense. We have the source data systems right at the top there. There's an import step, there's a calculation step, there's a reporting step, and then there's a distribution step at the bottom. So that kind of makes sense. But then it just goes completely crazy. So this thing here is really important because everything's pointing to it. I don't really know why, but it's definitely important. That's like London Heathrow or Amsterdam Schiphol, a big airport with lots of routes around the world. And then over here on the left-hand side, we've just got different shapes and colors and line styles and arrowheads and all sorts of craziness. And that box there says UI, upside down user interface. And the only reason it says that upside down is because in this example, somebody was sitting on the other side of the table. This one here represents every system you'll ever work on. So the big red box around the outside, that represents your system boundary. Inside your system boundary, you transport data in and out. You generate reports for important people. You do some auditing of events, maybe. You hopefully handle errors. You have some scheduled jobs, and you do business logic. I mean, this is a wonderful example of like a software architecture 101 diagram where it doesn't really tell you anything about the business domain whatsoever. Even just renaming that central box and calling it a financial risk calculator at least brings us back into the business domain that we're in here. This one here is what people often refer to as a logical view. And again, it's just really a list of things and the relationships between them. there's a risk calculation thing and a report creation thing and a security thing that seems to connect to a couple of different boxes. It doesn't really tell you anything. It's just that very high level, logical, fluffy, conceptual diagram. This one here really has no technology choices on it. And there's a very long discussion that we should probably have here about the importance of doing architecture and upfront design and also thinking about technology choices. But fundamentally, this diagram doesn't tell you about those technology choices. And the technology choices do have a huge influence on the resulting architecture. Since this is the Java use group, I'm sure you're familiar with POJOs, plain old Java objects. In the C# world, they have POCOs, plain old C# objects. This is the HOCO, the homeless old C# object. And basically, at the bottom of this diagram, there is a SQL Server database. There's an application at the top, console C#, it says. And then we've got lots of other boxes. There's a data loader thing, C#. Calculation manager thing, C#, risk calculation thing, again, C#. And I'm not really sure what this diagram is trying to show, but it seems to be showing lots of different levels of abstraction. And I think what I really want to do with this diagram is to draw a big box around most of the other boxes on this diagram to give those C# things a home. So I want to talk about some sort of containment hierarchy. This is another great example diagram. It's very cluttered, it's very complex, it's all one color. This is describing a much more kind of complex, event-driven, asynchronous style of architecture. And it's a bit like those books I used to get when I was a kid. They were choose your own adventure books. And basically you would start from page 1, you would read through like 10 or 20 pages, and then you get to turn to different pages in the book, depending on the story that you wanted to create. This diagram's the same. You start at the top, you go down through the picture. You follow the fail event, the complete event, the reject event. Now, when I read this book as a kid, my character always died, which was super annoying. And this diagram is kind of the same thing. No matter which path you take, you'll end up over here in this trap. So this is a really good example of where we need to strip off some information and maybe use color coding to show different paths through the system. One of the things I like on my architecture diagrams are people, because then I know how the human users, real world people, are interacting and using my system. But they need to have a name. Otherwise, like here, they're just faceless clones. They're like stormtroopers attacking your system somehow. This is why whiteboards are useful. So, we don't need this report repository thing. We'll cross it out. We don't need this line here. Oh, yes, we do. We'll put it back. Sorry. And we say that naming's hard. So, yeah, we'll do some renaming as well. And if you take this to a logical conclusion, you get something like this. So this started out, I think, as an entity relationship diagram. There's a crow's foot symbol there. And the box in the center, I think, was placed in the center because it was somehow important. And you can see that everything links to it somehow. But then this group scribbled out that middle box. And now the diagram is basically pointless. It's meaningless. So I have 15 or 20 gigabytes of photos like this from doing this workshop all around the world. And you might be thinking, well, surely, these are all hand-drawn diagrams. Maybe using a tool would help, and it doesn't. So when you use a tool, you get nice square boxes, and you can do gradient shading and have nice colors and line the boxes up. But fundamentally, using a tool doesn't solve any of the problems immediately, because you end up getting the same types of diagrams, but they just look prettier. Whenever I go to visit organizations around the world and they let me look at their documentation or their wiki pages on Confluence, these are exactly the types of diagrams that I see. And they exhibit all of the same problems that I've just summarized in those horrible diagrams. So what's the point of all this? Well, it's 2018. We're still talking about lean and agile and moving fast. And if you want to move fast as a team in the same direction collectively, you need good communication. So that's essentially all this is about. And I've run this workshop a lot. So I've been running it for about 8 or 10 years now. I've run it all around the world in 30 plus countries for about 10,000 people. The unfortunate thing here is that I don't have any empirical evidence to back anything up in this session. So I've done no academic research, no studies, but what I do have is a lot of anecdotal evidence, and I've witnessed and evidenced how people tend to visualize their own software architectures. And the conclusion I basically have is this: software architects especially struggle to communicate software architecture, and that's essentially the thing I want to fix, and that's what we're talking about this evening. So you might be thinking all this, well, hang on a second. There's something called the Unified Modeling Language, UML. And surely that's supposed to be the standard way to do this. So whenever I'm in front of a real life physical audience, I ask people, do you use UML? And the answer is not really. So when I've asked this question around the world, it's normally about 10% of people who claim to use UML in some form or another. I'm now seeing many, many more teams where this number is actually 0 people out of 10. So I've seen teams where literally nobody on the team understands UML at all. And it's worth pointing out here that even when I do see people using UML, they're normally only using class diagrams, sequence diagrams, state charts, and just the kind of basic stuff in there. So in order to answer this question and present some solutions, we need to step back a couple of steps. And I guess first of all, we need to figure out, well, who are the stakeholders that we need to communicate to? And also, what information do they need? And it turns out there are lots and lots of different people in any organization who might want to know something about the software systems that you are building. Some of those are very technical, so architects and other software developers, for example. Some are very non-technical. So I'm thinking about business sponsors, investors, management teams, that sort of thing. So ideally, what we're trying to do here is we're trying to describe our software system in a way that makes sense to as broad a range of people as we possibly can. The primary use for any diagrams and documentation for me is really communication and learning. So this is everything from describing what we are going to build, what we're planning to build. It could be describing what we have built, so creating post-implementation documentation. It could be for onboarding new members of staff, could be support or maintenance. There's a whole number of different reasons that we might want to create diagrams and documentation describing our software. There's also an interesting secondary use that we're not really going to talk about today, but I can point you to some other resources that tell you more about this. And basically what I'm saying here is, if your architecture diagrams are actually connected to your source code somehow, you can use those architecture diagrams as a way to basically do things like architectural improvement. And what I mean by here is to facilitate architectural refactorings. So none of this is really new. If we go back to the late 1990s, Philip Crutzen, who's one of the Rational Unified Process people, he created something called the 4+1 view model of software architecture. And he basically says to describe a software architecture, we use a model composed of multiple views or perspectives. For those of you who might not have seen the 4+1 model before, this is what the 4+1 model looks like. You have to remember the context of when this was created. So it's late 1990s. We're using a Rational Unified Process. We're capturing requirements as use cases, and each use case has a number of different possible scenarios through them. And essentially what we're doing here is we're taking our important scenarios that describe our system and how it works, and we're documenting each scenario from 4 different perspectives. So there's a logical view that talks about logical conceptual components, for example. There's a development view that shows how the logical components are mapped onto code. There's a process view that talks about things like concurrency and parallelism. And finally, there's a physical view that talks about infrastructure and deployment topologies. It's worth pointing out here that this is not the only way to do this. So some friends of mine, Owen Woods and Nick Rosansky, wrote some awesome books about software architecture that I definitely recommend reading. And in that book, they have a model they call viewpoints and perspectives. And what they've done is they've taken 4+1 and they've enhanced it and extended it to include different things. In doing this, they also renamed some of the 4+1 views because they thought some of the original names were slightly misleading, perhaps. Every book you read about architecture will do the same type of thing. They'll take a concept like 4+1 and they'll evolve it somehow. The issue I have with a lot of these different approaches is really the separation between the logical and development views. And you can see this, this is quite evident in a number of the different approaches to describing software architecture. And it's kind of worth stepping back for a second and pondering why that might be. And I think this is just one of those kind of traditional, typical things that we used to do as software teams. So imagine you have some requirements, you're designing some software. You hire an architect, the architect does some logical design, The logical design then gets handed over to a bunch of developers who do the kind of physical design. So I wonder whether that's where this logical development view has really come from in the past. Of course, we don't really do that so much anymore because we are delivering software in very, very different ways. And that's what I want to do as well with these architecture descriptions. I want to merge the logical and the development views together. The reason I want to do this is because I go and visit organizations and they show me these wonderful logical architecture diagrams, but then they say, these look lovely, but they don't match our code. And that's a huge problem, because if you do have these wonderful looking architecture diagrams on your walls and they don't match your code, what's the point of having them? They're essentially lying to you. They're useless. George Fairbanks wrote an awesome book called Just Enough Software Architecture. And in that book, he talks about this exact same problem. It's called the model code gap. That's the name he gives it to it. And the model code gap is essentially, imagine you have a bunch of architecture diagrams. On those architecture diagrams, you're going to be using terms and abstractions like modules or components or subsystems or layers. So these are the sorts of words we use to describe architecture. If you look at the code does not contain these same abstractions. So I'm guessing most of you listening are Java developers. In Java, there is no component keyword, is there? In Java, there is no layer keyword, is there? So what we typically do in Java is when we're writing applications and we want components or layers, we typically use things like packages or namespaces or modules or things like this. So there's some way that we structure our code, and that code structure somehow maps onto our architectural construct. When that's clear, all is good. But when it's not clear, this is when we get the model code gap. So when there's no clear mapping between a box on an architecture diagram and stuff in your codes, that's the model code gap. None of this is new again. So I found some academic papers from the late 90s. And this one here is called Bridging the Gap Between Source and High-Level Models. And just the first two opening paragraphs explain the whole thing. So essentially, if I ask you to now draw me some diagrams of the system you are currently building, you'll hopefully draw me a very high-level diagram, something that matches your mental model, something that matches the way that you perceive and think about your system. If I find some tooling to reverse engineer me some diagrams based upon your real code, I'm going to get a very, very different picture, aren't I? I'm not going to get the high-level picture with modules and components and layers. I'm going to get something that really reflects classes, interfaces, namespaces, packages, folder structures, for example. The two diagrams are going to be very, very different. It's the model code gap thing again. To step back even further, we need to really go back to think about vocabulary. And it turns out even now in 2018, we don't really have a common vocabulary to describe software architecture. Now, this potentially sounds like a bit of a crazy thing to say, but let me just run you through a couple of quick examples. So this is a map of London. The blue thing running through the map of London is the River Thames. And we can go and look up what a river is in a dictionary. A river means it's a flowing body of water, flows one way or the other, depending on topology and tides and all that sort of stuff. So given that we know what a river is, and we know how it's typically represented on diagrams, we can use this knowledge to go and explore the landscape and find other rivers. So we know how to identify a river in real life. This picture here is a kind of top-down floor plan for a bathroom. And this thing here, which I'm highlighting now, is a toilet. Now, we hopefully know what a toilet is. Again, this is something that we learn hopefully at an early age. And we can use this knowledge to walk around a building and find other toilets. If there are any electrical engineers listening, there are a number of ways to represent circuit diagrams. There's a kind of funny, cartoony, pictorial version, and there's this schematic version. This thing down here, this zigzag, it represents a resistor. And again, we know what a resistor is. Some of us do anyway, I don't. And if I was to give you a box of electrical components with resistors and capacitors and switches and LEDs, I'm pretty sure that a lot of people could find a resistor in that box and hold it up. And if you knew the color coding of the resistor, the stripes, you could tell me how powerful that resistor was. So again, this is something we can see on a diagram, and we know how it's represented in the real world. If we switch back to software again, this is a UML component diagram. There are a couple of major versions of UML, UML1 and UML2. I forget now which version this is, but this is a UML component diagram. And given that this is a UML components diagram, it should come as no surprise, hopefully, that each of these boxes on this diagram represents a component. And that's fine, that makes sense. But when you look a bit more closely at the diagram, it's not really clear what each of these components actually is. So this thing down here, the University DB, that has a database stereotype. So this looks like a database, like an Oracle database. And you can see it has a JDBC interface hanging off the right-hand side. We have a couple of infrastructure components. I'm not exactly sure what that means. On the left-hand side, we have a seminar management component and a student administration component. And these are both stereotyped UI, so user interface. But I'm not sure if these are web applications, so, single page applications running in the browser or static HTML, or they could be mobile apps, or they could be desktop apps, who knows? They're just some sort of generic UI. And the components in the middle, I really don't know what these are at all. I don't know whether these components sit in the UIs or sit in the database. I don't know whether they are separately deployable, like a microservice, or whether there's something that's bundled into some more monolithic application. So there's not enough information on this diagram for me to accurately figure out what this diagram is actually showing me. This is another example I like to use, and again, it's another component diagram, and we have all sorts of different components representing all sorts of different aspects of this software system. Everything from XSL style sheets, web servers, and my favorite is the business logic component. Again, this is meaningless. It doesn't really mean anything. To boil this problem down to its absolute essence, if you go and look up the word component in a dictionary, it literally means, part of something bigger. And that's a problem because when we use the component in the software world, we can use it to mean very different levels of abstraction and detail. So imagine we are building a software system, and the software system is comprised of a web application talking to a relational database. We could say that the web application is a component of the entire system. That makes sense using the dictionary definition of that term. We could also say that the logging component is a component of the web application. So again, we can use the same word for different levels of detail, different levels of abstraction. If you've heard of domain-driven design, DDD, one of the things DDD does is it tries to create a ubiquitous language between us as developers and the business people, so that when we're talking about the domain, we use the same common ubiquitous language. The irony of this is that although that works really great, we as software developers do not have our own ubiquitous language to describe software architecture. And that's the thing that really needs fixing, in my opinion. So we have two things to look at for the rest of this session. The first is abstractions, and the second is notation when we're drawing diagrams. So my recommendations around abstractions are really, if you're drawing a diagram, ask yourself this question. So if you're drawing a diagram during an upfront design exercise, ask yourself the question, does the diagram reflect how we would actually go and code that thing if we were asked to? And if you are drawing diagrams that retrospectively document an existing code base, ask yourself the question, do the diagrams reflect what we really have in the code base? So my top tip here, and this sounds a bit counterintuitive, is when you're drawing architecture diagrams, don't think like an architect, think like a developer. And the reason I say this is because when I'm creating architecture diagrams, the audience, the primary audience for my architecture diagrams is other developers. And so that's who I want to target predominantly. And so I want diagrams that inherently make sense to us as software developers. We could look at UML, and if you do look at UML does have a common set of abstractions, and it also has a common notation to describe those common abstractions. One of the problems I see with UML, and well, not really UML, but the way it's used predominantly, is that people normally abuse UML. And a really good example of this is I often see teams drawing UML class diagrams, and they use the boxes, the classes, to represent something that's not a class, like a software system or a message bus or some piece of infrastructure. And they're doing it just because it's a box and they can put a name in the box. So I think what we should do instead is really to, again, backtrack, step backwards, and to figure out what the abstractions are first. So we find a common set of abstractions that works for us and how we want to describe software, and then we let the notation evolve separately. And again, this might sound a bit foolhardy, but if you go and get two local maps of your area and lay them out side by side, and tourist maps are great for this, you'll see that the two maps will show the same types of things. So the same places, the areas, the districts, the shopping malls, the train stations, the bus routes, the fields and the countryside and all that sort of thing. So that, two maps of your local area will typically show you the same things, the same abstractions, but they might use a different notation to do that. So different shadings, different colors, different icons, different symbols. How do we decipher the maps? Well, there's a key or a legend in the corner, and this is literally the key to unlocking what the diagram is showing us. So a real-world map is a really nice, simple example of where we have a common set of abstractions and a varying notation. And that's a super powerful concept that we can take into our world as well. So let's start with abstractions. So imagine you are building as a team a software system. So I'm going to say that a software system is made up of a number of containers. Now, it's a bit unfortunate that Docker got popular because this is not necessarily a Docker container. And if you go onto a website I'll refer you to later, it kind of explains why the term container was chosen. But essentially, a container is a separately runnable or deployable thing. In the real terms, it's something like a client-side web app running in your browser, a server-side Spring MVC web app, for example, a Java console application, a mobile app, maybe a microservice, some sort of database schema, a file system, and so on. So it's something that needs to be running for your system to work. If we zoom into the containers, I'm going to say that they are made up of components. So I do want to use the word components, but I want to use the word components to mean, a grouping of functionality with a nice simple interface running inside a container. Because we're talking about Java here, most of the systems I deal with are Java. If you look inside my components, they are basically made up from code elements like classes and interfaces. And that's a really simple hierarchy to think about the static structures of a software system. So a software system is made of containers. Containers contain components. Components are built from code elements like classes. Once you have that abstraction, that set of abstractions in your mind, you can then draw some diagrams. And this is what I refer to as my C4 model. And you can find a lot more information about everything I'm about to talk about on c4model.com. So essentially, there are 4 layers of diagrams here. And I will show you some examples shortly. There's a system context diagram. There's a container diagram, a component diagram, and then optionally some code diagrams like UML class diagrams. And what I'm really trying to do here is create a set of maps on top of a code base. So the first 2 levels allow you to get an overview of the things being built. If you want to know something about the implementation details, you can zoom in a little bit more. And if you really want to get down to the nitty-gritty implementation details, you want to see what the code looks like, then you can kind of get that detail on demand. So whenever I'm describing the C4 model, although the number 4 is in the name, I typically only create the first 3 levels of diagrams. And it's really diagrams and maps. So I'm trying to create a set of diagrams on top of a code base with different zoom levels, because then this allows you to deal with complexity. So the hierarchy allows you to deal with complexity, and you can tell different stories at different zoom levels to different types of people. So that's the concept in a nutshell. It's worth also pointing out here that I'm really only talking about static structural diagrams at the moment. And the reason I do this is because once you do understand your static model, so software system down to level of code with a couple of levels in between, you can draw other diagrams using those same concepts very, very simply. So I'm not going to talk about deployment and behavioral diagrams, but there's more information on c4model.com if you're interested. So some examples. For those of you who are not in the Java world, there's a framework called Spring, and Spring does everything. That's literally all you need to know about Spring. That's what they tell me anyway. And part of Spring is called Spring MVC. It's a web model view controller framework for building server-side web applications. And there's a sample application that the Spring team shipped called the Spring PetClinic. And it's a very, very simple little application. Imagine you work for a pet clinic, a vet, an animal hospital. It's essentially a management information system, so you can get information about vets and pets and owners and visits and that sort of thing. So this is diagram 1. This is a system context diagram for my Spring PetClinic system. And all this is showing is basically, the Spring PetClinic system is the thing I'm building. So this is my software system. And there's one type of user, a clinic employee, and the clinic employee uses the system. So this is a really super simple example of a system context diagram. And the system context diagram is simply showing the system we are building, the Spring Pet Clinic, and all of the people who use it. So that's diagram number 1. If we zoom into the Spring Pet Clinic system, we get to see the containers inside it. So now, if we look at this in a bit more technical detail, the Spring Pet Clinic system is made up of a Java and Spring MVC web application, and that talks to a relational database. So again, this is a nice simple code base, and literally this is just a web app talking to a database. If we zoom in to this container here, this web application, we get to see inside it, and this is the component diagram for the Spring Pet Clinic web application. So there's a bit of a backstory about how I came up with this diagram, which you can find some more information online about. But essentially, each of these boxes inside this this dashed box, each of these boxes represents a component within the Spring Pet Clinic web application. So there are a number of controller components, there's a clinic service component, and there are a bunch of repositories. So again, it's a nice simple set of diagrams, a nice simple set of hierarchies that allow you to zoom into different levels of detail. Just so we can cover off the UML thing, the diagrams I will show you are mostly boxes and lines notations, and I will talk about some tips for notation later. But if you do want to use UML, the C4 model is kind of notation independent. So here's another couple of examples of a system context diagram using UML. There is no system box in UML. So really what you have to do is you have to draw an actor, and then kind of using arrow towards a component, in this case with a software system stereotype, or you can use a package symbol. So UML gives you a bunch of different options, and you kind of have to pick the one that you like the most. So that's the system context diagram. If we zoom into the system boundary, this is an example container diagram drawn using UML. So it's the same thing. It's the clinic employee using the web application. The web application talks to the database. And here I'm using a package to represent the software system and sub-packages to represent each of the containers, the web app and the database. If we zoom into the web application, again, this is the component diagram for the Spring Pet Clinic web application. And this, this is where it does make sense to use a UML component diagram, because each of these boxes is really a UML component. And what I've done here is I've used a stereotype to say exactly what type of component each of these things are. So that's a Spring service there, Spring MVC controller, Spring repository. So again, you have a bunch of options around notation when you're describing your architecture. So that's a nice simple example. I want to show you a couple more examples to illustrate a couple of other different aspects. So I live in Jersey in the Channel Islands, and when I moved back to Jersey in 2008, I wanted to find other tech people and basically keep a list of them. So I built this thing here called techtribes.je. This is no longer available. It kind of served its purpose. But at the time, it was a simple content aggregator for the local tech industry. It listed local people, businesses, blog posts, news, events, and so on. So this is a system context diagram for my TechTribe system. So this box in the center, that's my system. That's, that's the thing I'm responsible for. That's the thing I own. That's the thing I built. TechTribes had 3 different types of users. So if it was still running, you could go onto the site right now and you would be an anonymous user, and you could view the content on the site essentially. Because my content was aggregated into the site, I could sign in with my Twitter ID and manage my user profile. So that's me. And there was a super secret administration user. So these boxes at the top represent people, personas, actors, roles, however you want to think about people, that's what those top boxes represent. At the bottom are my key system dependencies. So what other systems does TechTribes depend on for it to do its job properly? So we're pulling profile information and tweets in from Twitter. We're using the GitHub API to pull back information about people's public repositories. and we're also subscribing to people's blogs. So again, essentially, this is Tech Tribes and how it fits into the rest of the world. There's not much technology on here. It's just a nice high-level starting point. If we zoom into the Tech Tribe system, we get to see the containers inside it. So this is the container diagram for the Tech Tribe system. At the top, we still have our people, and at the bottom, we still have our other systems. All I've done here is I've expanded out and zoomed into that Tech Tribes box to show the containers inside it. And very simply, at the top, there's a web application. This is a Java Spring MVC web application running on Apache Tomcat in this case. And that's a single point of access for all of the different user types. At the bottom is a content updater. This is a separate standalone Java 7 console application. This was written a few years ago, as you can tell. And this is the thing that connects to Twitter, GitHub blogs, and pulls the data back. It then stores the data either in a relational database, in this case MySQL for most of the data. On the other side, there's a Mongo database for storing the tweets and the blog posts. And there's a file system in the middle, which a bunch of search indexes get stored on. So this diagram is showing you what the separately runnable, deployable things are that make up the Tech Tribe system. So in other words, imagine you joined my Tech Tribes project. You would have to have these things running on a laptop, in other words, in order for the entire system to work. What this diagram is not showing you is anything about clustering, scaling, failover, availability, data centers, disaster recovery. So all of that information we save for a separate deployment diagram that I'm not going to talk about. Let's say you join my project and you want to work on this content updater thing here. So again, let's zoom into that and show the components inside it. So this diagram is the component diagram for the content updater. The content updater is basically this dashed box, and all of these boxes here are the components inside that content updater. The content updater talks to the outside world, so we'll still have our systems at the bottom. And the content updater stores information in these various containers up here, the two databases and the file system. And very simply, we can see that there is a scheduled content updater component in the middle. This is a Spring scheduled task. It gets kicked every 15 minutes. It uses a Twitter connector, a GitHub connector, and a newsfeed connector to connect to the outside world. And then it uses these other components up here to push stuff into the other data stores. So this diagram is really showing you, the components within the code base. I'm also starting to show you more about the low-level implementation details. So that's a Spring Bean using JWC. That's a Spring Bean using the Twitter for J library, and so on and so forth. I'll talk about notation in a second, but you'll see there's this logging component lurking over here. And this is really just a Spring Bean and a wrapper around log4j in this case. This logging component is actually used by everything. But what I didn't want to do is draw lines from everything to it, because then you get a very cluttered diagram very quickly. So I added, in this case, a black asterisk, the star there. What does that mean? It's used by all components. So again, you have some flexibility around how you want to describe architecture and the notation you use to do that. Let's imagine you are asked to go and modify this tweet component. You zoom in, and maybe this is what the class diagram of that tweet component looks like. So again, this is just a simple example of drilling down to that fourth level, showing you, in this case, classes and interfaces. I don't normally do this. I'd only tend to do this on large or complex components, or where I specifically want more information. It's worth pointing out that this last level you can often just generate straight from your IDE. So that's example 2. A third example I want to run through quickly is a quick fictional internet banking system. So let's imagine you work for a bank and you are tasked with building an internet banking system. And let's say this is for personal banking customers, and it allows them to look at their bank accounts, make transactions, make payments. So this is an example system context diagram for an example internet banking system. So this box here represents the internet banking system. That's the thing that we are going to build. We have different, in this case, we have one type of user. It's the personal banking customer. They use our system. Our system, our internet banking system, is actually going to get all of the information from an existing mainframe banking system. So maybe, this is the record of store for the bank, and this is the system in which all of the account information is held. Our internet banking system is also going to use our internal, in this case, Microsoft Exchange email system to send emails back to our users. So again, a nice simple context diagram. It's showing the system we are building and how it fits into the rest of the environment. So here I'm starting to use some different shapes, some different colors to represent different things, and I'll tell you more about the notation later. If we were to zoom into the internet banking system, again, we get to level 2, and now we get the container diagram. And this is a bit more complex than the previous examples because I wanted to show something specific here. So this is the container diagram for the internet banking system. So the personal banking customer, let's say that they use a web application. Let's say this is a Java and Spring MVC web application. So this is running on the server and it's delivering static content back to the user's browser. Let's imagine that the internet banking system was actually a kind of rich single page application written in JavaScript and Angular. From a deployment perspective, of course, you would probably bundle up all of that JavaScript into your backend server-side web application. But from this perspective, from a container perspective, it's really a separate application because it's running in a separate place. It's running a separate process space. So this is the backend server-side web application, and this is the kind of browser-side, client-side single-page application. So I wanted to just show a simple example of why I use the word container here. The word container is really a generic term to mean something that kind of runs or stands alone. There's also a mobile app here, so maybe the personal banking customer can use a mobile app. Maybe that's written in Xamarin. And both the single page app and the mobile app, maybe they use a backend server-side API application, through a kind of JSON or HTTPS API. That itself uses a database, so maybe we store all of the user registration information in a database like Oracle or MySQL. The API application then maybe makes calls to the mainframe banking system to go get information about accounts, make payments, and then it's using the email system as well. So again, a slightly more complex container diagram showing responsibilities, technologies, and that sort of thing. Let's imagine we were working on the API application. We zoom into that thing, and now we get to see the components inside it. So the API application is used by the single page app and the mobile app, and the API application uses the mainframe banking system and the database. So one of the things you should notice is that when you zoom down to different levels of the hierarchy, the relationships still make sense. That the relationships on each diagram at different levels of detail are basically the same. And here we can see that maybe there's a signing controller. Maybe this is a Spring MVC REST controller. There's some sort of accounts summary controller. So maybe that's providing a nice API to get information about accounts. That might be using some sort of backend. The account summary controller might be using some sort of mainframe banking system facade. So maybe we've wrapped up all of the connectivity logic to the mainframe system into that thing there. If we zoom into that mainframe banking system facade, again, we start to get down to the code. And this is a sample example class diagram of what that code might look like. So maybe there is a mainframe banking system facade component, and all of these different classes are used in the creation of that component. So again, different levels of diagrams to tell different stories to different audiences. So just to wrap up, I want to talk about notation because I've not really spoken about that much. Some tips for you. Whenever you're drawing an architecture diagram, you should have a title on every single diagram. And this should be short and meaningful, and it should really include something about the diagram type and also the diagram scope. So if you are drawing a system context diagram for the financial risk system, make sure the title of the diagram says exactly that. So something about the diagram type and something about the scope. And this sounds like a really silly piece of advice, but nobody does it unless you prompt them. And once you have a title on the diagram, it kind of sets the reader up. They know what to expect. In terms of layout, if you don't have access to a whiteboard at work, you can use sticky notes and index cards to represent boxes. You can move the index cards and the sticky notes around. So, if you want to have a first go at creating a nice diagram now, either use a tool or use sticky notes so you can move these things around. People often ask me, which way do you draw your diagrams? Do you draw people always at the top and databases at the bottom? And, it doesn't really matter. What I try to do is I try to put the most important thing, so the scope and the focus of my diagram in the center, in the middle, and I try and work around it, being consistent across diagrams if I possibly can. So if I do create a diagram with people at the top, when I'm showing other diagrams with people at the top at different zoom levels, I will try to have people at the top as well. Acronyms, it's really, really common to see acronyms and diagrams. And there are two types of acronyms that you should really be wary of. There are technology acronyms like MVC and JDBC and JMS. if you are definitely targeting developers, you can probably get away with the technology acronyms. If in doubt, have a glossary, have a key or legend to describe that stuff. The acronyms that really worry me the most are the business or domain acronyms, because they tend to be a bit more harder to get into, especially if you're joining an existing organization. Elements. So my recommendation here is to start with simple boxes. And once you have a diagram that makes sense with simple boxes, then start adding shapes. So what do my simple boxes have in? Well, you might have noticed from my example diagrams that my simple boxes actually have quite a lot of text in. So there's an element name. I'm always very explicit about the type of that element, whether it's a software system or a container or a component. If it's appropriate, I'll also list the technology choice in there, and then I'll always have a description or a set of responsibilities for that thing. One of the things I don't want you to take away from the session is that Simon says we must always use his notation. This is the notation I use because it's very simple and it works on a variety of different tooling and whiteboards and sticky notes. Essentially, every box I'm trying to represent, so people, software systems, containers, components, they have name, type, and descriptions. Use whatever notation you want, but just make sure it makes sense. The reason I add all the text on the diagrams is because the diagram on the left is typically what people draw when you ask them to draw an architecture diagram. And essentially, it's just a list of named boxes. And, we have this file system box here, and that's just ambiguous, what's being stored on the file system and why. So I add more text to my diagrams, and especially the thing about descriptions. What that really does is it gives you a much, much better at-a-glance view of, what something is or what it does or what it's there for. So key recommendation here, add more text to your diagrams. In terms of the lines, we always forget about the lines, but the lines are super important because the lines glue the boxes together. I would recommend favoring unidirectional lines. So this means one-way arrows. And you can either show dependencies or data flow. That's entirely up to you. And what I recommend is that, again, all lines should have some sort of description to describe their intent. So once you start asking people to draw unidirectional arrows, they always ask you which way do you draw the arrows, and it's entirely up to you. So with the architecture charter that I present to people, the financial risk system is essentially getting data from the trade data system. So the financial risk system gets trade data from the trade data system is a very, very good way to write that the link between the two systems. You could also express the same link by flipping on its head. So you can say that the trade data system sends trade data to the financial risk system. So you can talk about dependency or data flow. It's entirely up to you. A really good tip for creating relationships or drawing relationships that make sense is literally just to read your diagram out aloud. So here we can see that the web application reads from and writes to the database. You'll notice there's some extra wording here, from and to. These are, in English, these are called prepositions, and they tell you something about the direction of the relationship. So read your relationship out loud. If it makes sense, you're in a good place. Always have a key or a legend on your diagrams to explain any notation you're using, so shapes, line styles, colors, borders, acronyms, and so on, even if the notation seems obvious to you. So that's something I can't stress enough. And I would also argue that even if you're using a standardized notation like UML or Archimate, you should also still use a key or a legend, because after all, not everybody's going to know those notations. So here are a couple of example keys and legends from the diagrams I showed you previously. So this is the component diagram for the Spring PetClinic web application. You can see that this dash box here represents the web application container. We have the database, the person, the clinic employee, and then I've used different colored boxes to represent different types of components. So the controllers are colored differently from the services, which are colored differently from the repositories. So again, you can now, once you have a diagram that makes sense, you can use color coding to superimpose some additional information on top of that diagram. Here's the internet banking example. Again, you can see what I've done here is I've used different colors to represent, the system we're building and existing systems. So the blue versus the gray, for example. And again, you can add this additional supplementary information once your diagram already makes sense. And that's another important point here. I am using shapes, colors, and size of boxes to complement a diagram that does already make sense. So one of the things you should be able to do with any diagram is take away all of the color, take away all of the shapes. And if the diagram still makes sense, then again, you're in a good place. The reason I talk about shapes and colors, and the reason we tend to prefer shapes and colors is because, you know, it makes the diagrams more aesthetically pleasing. But here are two example diagrams showing the same thing. This is a different variation of the techtribes container diagram. The diagram on the left is just colored boxes. The diagram on the right now has some additional shapes. There's a kind of cylinder shape and a folder shape. Most people will instinctively prefer the diagram on the right because, you know, especially at a distance, and there's no way you can read the text here, of course, you can start to see that, oh, at the top, those look like people, and there looks like some database type things there. But fundamentally, the two diagrams have, you know, no additional information when compared to each other. So a couple of final tips. What I urge people to do is really to increase the readability of their diagrams so that the diagrams can stand alone. And this is a somewhat controversial point sometimes, but whenever I see a software architecture diagram, it's always in a presentation or on a wiki page or on a website, and the author is never there to narrate or describe that diagram. So I want to put as much information as I possibly can on my diagrams so that when they do stand alone, they still make sense. But I don't want to spend hours and hours and days doing this. So this should be something we can do quickly. And any presentation we provide, any narrative we give, again, should complement, it should tell a story on top of the diagram that already makes sense. And really, that's that. So what I've presented here is a very, I think, simple approach to describing and diagramming software architecture. And really what I'm trying to do here is remove the complexity that many teams associate with diagramming software. Because when you're tasked with an upfront design exercise, you should be putting all of your brain power into doing the design exercise and not figuring out how to communicate your ideas. So using something like the C4 model, you know, it's a nice simple framework, and there are some nice easy tips there to create much better software architecture diagrams. So the final takeaway really is abstractions first, notation second. Whenever you go back to your teams and you start creating diagrams, stop, pause, figure out what types of abstractions you want to use to describe your static structure, and then let your notation evolve as a secondary thing. You know, make sure your team has ubiquitous language to describe their architecture. And that's me. So thank you very much for listening. I think we've got some Slack questions maybe, so I will hand it back over to you.
Yeah, thank you, Simon. This was excellent. I didn't know what to expect coming to this session, but it was absolutely great. Starting from the hilarious diagrams that you showed in the beginning, and then kind of like just, it sounds so easy when you say that, right?
It does, yeah, but it's never that easy, right?
Yeah, so we have a couple of questions. Let me just urge people to ask more questions. If you are watching this live and if you're in the Slack, please ask questions. So we have one from Nuno Simoes. Sorry for that name pronunciation. So the question is, what if our system is this large that we need to have subcomponents of the components, and then subcomponents of the components,
right,
and so forth? Yeah. So don't we have the same problems of not using the ubiquitous nomenclature or something like this? Will we?
Yeah, so there are two basic approaches for dealing with really large systems. The first approach, and this is the approach I don't like, is to introduce new abstractions into that hierarchy. So things like subcomponents or supercomponents or subsystems. So when you are thinking about creating your set of abstractions, if you do want to introduce more layers to you know, group things together, and that makes sense, then that's absolutely fine. But just make sure that's written down somewhere, because when you draw the diagrams, you know, each diagram should map cleanly onto one of those abstraction layers. The other approach, and this is the approach I prefer, is rather than showing, so let's say you're building a microservices architecture with, 100 microservices. There's no way you can draw those 100 services on a single diagram, right? So what you do instead is you stick with the levels in the C4 hierarchy, and rather than draw one diagram with 100 microservices, you draw maybe 4 diagrams with 25 each. So you partition your diagrams according to vertical slice or ownership or business concept or bounded context or something like this. So yeah, a couple of different options for dealing with size and complexity.
Excellent. While we wait for questions, I see someone is typing. I have this weird one. If you had to recommend, I know that you've written books, so like we definitely should read those. But if you had to recommend one resource that is consumable in, say, 8 hours, imagine someone is preparing for the architecture visualizing meeting tomorrow, and they have like one night to prepare. What should they do? What should they read or watch or?
So you're right, there are lots of books out there that talk about visualization, and some of them are quite in depth. So if you look at the SEI books, there's a lot of material in there, and there's there's a lot of advanced concepts. There's a whole bunch of ISO and IEEE standards around doing this as well. They don't tend to be used as mainstream as other mechanisms. So I'm going to say read my 2 books, because I know it sounds awful, but my 2 books are the first one's like 90 pages and the second one is 200 pages. So they're very, very quick to kind of flip through.
Okay, yeah, that's definitely doable. At least like 90 pages, definitely doable through a night.
Yeah.
Excellent, thank you. And there
But
is
c4model.com is a good starting point for all of the diagramming stuff.
And there should be no shame in actually recommending your books. You put enormous time into writing those, and people should read them.
Yeah.
So Sean Smith is asking, is there a shape template library that you can recommend for tools like Lucidchart or to get started with C4?
Is there a shape template library? No, so not for Lucidchart. So if you go to c4model.com and you scroll right to the bottom of that site, there's a tooling section, and there's a bunch of different ideas for tooling there. So I also have my own tooling that I've not spoken about, but there are templates for OmniGraffle and templates for draw.io as well. So c4model.com, scroll to the bottom and have a look at the tooling options there. And of course, if you want to contribute a shape library for Lucidchart, feel free, let me know, and I'll add it to the site.
Excellent. Yeah, there are plenty of tools. I think I haven't heard of Structurizer, or I just
so Structurizer is my own tool. It's a very opinionated modeling tool.
Okay, that's very cool. Yeah, I've heard something about that. I cannot say what I've heard. Maybe I just stumbled somewhere in Twitter on that. But yeah, well done.
Nice.
Yep. I don't think we have any more questions. We might have, but if we don't, thank you so much once again for this session. Thank you for taking time to be with us. If you are watching this later on YouTube and you haven't seen the whole session yet, this was Simon Brown, and you can find him and ask all the questions that you didn't have time to ask during the session on Twitter, and where he goes by @SimonBrown. So yeah, I hope you enjoyed the session. We're gonna make more Virtual Jug online meetups this year. Stay tuned for that. Thanks again. It was a pleasure to host you here, Simon.
Thank you very much as well. Thanks everybody for listening.
Thank you. Bye-bye.